Each year, Thayer School also recognizes a graduate or friend of the Thayer School with the Robert Fletcher Award, given in recognition of distinguished achievement and service in the highest tradition of the school. When Robert Fletcher was selected by General Sylvanus Thayer and Dartmouth President Asa Dodge Smith to become Thayer School's first professor and dean in 1870, he was a 23-year-old Army lieutenant serving as an assistant professor of mathematics at the U.S. Military Academy. Over the ensuing 65 years of service to Thayer School and the neighboring community, Fletcher was to leave a strong, lasting impression on generation after generation of students. His accomplishments as director and teacher almost invariably merged in the minds of students with his quality as a human being. As Sylvanus Thayer was the father of the U.S. Military Academy at West Point, so was Robert Fletcher the father of the Thayer School of Engineering at Dartmouth College. In addition to leading the Thayer School, Fletcher designed and supervised construction of steel bridges across the Connecticut and White Rivers and waterworks for the towns of Hanover and Enfield. For more than 40 years, he was president and engineer of the Hanover Water Company, as well as a member of the New Hampshire State Board of Health. His many activities contributed importantly to the prestige of the Thayer School, the betterment of his community, and the advancement of engineering education. The individual selected to receive Thayer School's Robert Fletcher Award must possess the qualities exemplified in the life and work of this remarkable individual. Today, we are honored to present the Robert Fletcher Award to Dr. Subra Suresh. Dr. Suresh, who had been nominated by U.S. President Barack Obama and was subsequently unanimously confirmed by the U.S. Senate to serve as the director of the National Science Foundation from 2010 to 2013, is a distinguished scientist and engineer who will become president of Carnegie Mellon University on July 1st. As NSF director, Dr. Suresh's initiatives included developing new programs to support research, education, and the careers of aspiring scientists and engineers, such as the Integrated NSF Support Promoting Interdisciplinary Research and Education Program, known as INSPIRE, the NSF Career Life Balance Initiative, the Graduate Research Opportunities Worldwide Initiative, known as GROW, and the NSF Innovation Corps, or I-Corps, familiar to many of us here at the Thayer School. Previously, Dr. Suresh served as Dean of the School of Engineering and as the Vannevar Bush Professor of Engineering at the Massachusetts Institute of Technology. His experimental and modeling work on the mechanical properties of materials, innovations in materials design and characterization, and discoveries of connections between cellular nanomechanical processes and human disease have shaped new fields at the intersection of traditional disciplines. He has co-authored more than 240 journal articles, registered 21 patents, and written 3 very widely used material science textbooks. Dr. Suresh, who received his Bachelor of Technology degree from the Indian Institute of Technology in Madras, Master's degree from Iowa State University, and Doctor of Science degree from MIT, is the recipient of numerous awards and honorary degrees. He is a member of the National Academy of Sciences, the National Academy of Engineering, the American Academy of Arts and Sciences, and 7 other National Academies of Science and Engineering in Sweden, Switzerland, Spain, and India. Dr. Suresh, it is our pleasure and privilege to present you with the Robert Fletcher Award.
Thank you very much, Dean Helble. Good morning, everyone. I would like to offer my congratulations to the graduates and also to the families and friends who are here today. I congratulate you on having completed the Thayer School's rigorous courses of study in engineering. This is a day of well-earned pride and joy, and I'm most grateful to all of you for the honor and privilege of being part of your celebrations today. As I look out at this gathering, I'm reminded of the old joke that a graduation ceremony is an event where the commencement speaker tells thousands of students dressed in identical caps and gowns that individuality is the key to success. But where you go from here is a very individual matter. It's hard to predict where you will end up. When I graduated from college in 1977 with a bachelor's degree in engineering from the Indian Institute of Technology in Madras, I set out for Ames, Iowa to Iowa State University to get a master's degree with a one-way air ticket purchased with borrowed funds, a half-full suitcase, and less than $100 in my pocket. When I arrived in Iowa, I certainly never imagined that my career would subsequently take me to be the Dean of the School of Engineering at MIT and the Director of the National Science Foundation. By now, I'm sure all of you have figured out why I speak with a strong Iowa accent. And now, like you, I'm about to take a new step as president of Carnegie Mellon University. So I too am looking at a new phase of my life at this point in time. But I strongly believe that there is no group of Dartmouth's many distinguished graduates this year that will have more influence over the future of our planet than you will. We engineers have a reputation for being a bit too modest and low-key. But many people believe that we are more important to society than ever before. Countries large and small, from China to India to Singapore to Qatar to Rwanda, view innovation and engineering education as a ticket to economic prosperity to make a positive difference in the lives of millions of citizens. The National Academy of Engineering in 1999 published a list of the 20 greatest engineering achievements of the 20th century. You can probably guess what these include: the spread of electricity, the invention of radio, television, and the internet, the development of the petroleum industry, and along with that, the spread of automobile and construction of highways, the achievements of nuclear engineering and nuclear power, and the revolution in agricultural technologies. All of these brought enormous benefits to human life on a scale previously not imagined, and many of them were adopted in the lifetime of your parents and your grandparents. Then in 2005, the National Academy of Engineering issued another list. This time, the 14 greatest engineering challenges of the 21st century. In that list, you can see that here are a few items. Develop carbon sequestration methods. Restore and improve urban infrastructure. Engineer better medicines. Prevent nuclear terror. Secure cyberspace. When you compare these two lists, there is something very striking. And what is striking is that a great many of the challenges of the 21st century are issues that arise out of the engineering achievements of the 20th century. The success of the petroleum-based economy we built over the last century has given us the problem of how to control carbon emissions and slow climate change. The invention of nuclear technologies now leads to the challenge of preventing nuclear terrorism. The spread of instant global connectivity made possible by the internet now presents the challenge of securing cyberspace, preserving citizens' privacy, and protecting confidentiality of personal information. And the aeronautical engineering that transformed global transportation also means that infectious diseases can travel fast from anywhere on the planet to anywhere else, almost at the speed of sound. And they threaten the planet with a deadly pandemic if we are not careful. So my challenge to you today, the Thayer School's class of 2013, is this. What do we engineers need to do differently in the 21st century compared to what we did in the 20th century in order to respond to the challenges of our lifetime while also doing a much better job at anticipating future consequences? I want to offer 3 insights that might help in answering this question. The first insight: we must recognize and allow for the human factor and human behavior in our engineering solutions. The interface of engineering with social, behavioral, and economic sciences is now essential. We must recognize that incentives for human behavior must be anticipated and planned for, and the impact of technological capacities on social life must be better understood. Let me give you an example. In the late 1980s, the National Science Foundation, NSF, established its first engineering research center in the state of Oklahoma to develop weather forecasts and models that would predict severe weather events such as tornadoes. That center, over the years, has done wonderful work in developing simulation tools that accurately predict severe weather events. As you know, sadly, during the past year and just last week, citizens of Oklahoma died as tornadoes repeatedly pummeled that state. This tragedy arises not just because of our inability to predict accurately how tornadoes develop and move. Many technological advances have been made to address those predictions, and they are possible today to predict. It is also due to our inability to predict how people would respond to warnings about weather events. That's where the human factor comes in. The second insight I would offer is that we are in a new era of engineering with many new tools, and we must make careful and thoughtful use of these tools. So when I was at NSF, I was asked the question, what is so exciting about science and engineering now in the year 2013 compared to 10 years ago, 20 years ago? So during the last few years as director of NSF, I had a front row seat on progress across all fields of science and engineering. I learned that we are in a powerful new era, your era in a sense, an era defined by amazing new capacities. And we can put all of them into 2 broad categories. It is first of all a new era of observation. Today we have telescopes that show us the farthest reaches of the solar system, and we have microscopes that can show us materials at the tiniest sub-nano scales where we can observe them, manipulate them, and design them to make materials one atom at a time. We have computational simulations that give us glimpses of the origins of the universe. We can look at and listen to the depths of the oceans across the whole planet. Imaging technologies are giving us even more nuanced picture of the biology of a single neuron in the human brain, which can now be interpreted in conjunction with the psychology of the human mind. The second exciting thing about this era is that it is also a new era of data and communication. Communication technologies have also changed the definition of who can collect data. Any citizen with a mobile device can now take part in observation of a range of events. The approach of a tornado, the flight of a songbird, or the precise patterns made by a detonating bomb in Damascus or in Boston. Citizens are making more observations in more places than ever before, and with much greater accuracy than ever before. These will be useful for the advancement of knowledge in science and in society. We are indeed at a time when a young child in a rural village in Brazil can use a mobile device to observe the sky and generate data that feeds into a national or international network that becomes part of a scientific data gathering by established scientists. An iPad that you and I have can now generate up to 1 terabyte of data per day. So as engineers in this new era, we have many challenges to address that intimately link the latest in technology with human behavior. Here are some questions. How do we take the vast amount of data generated every day and make sure that we are able to sort, organize, store, retrieve, and permanently archive information across rapidly changing platforms? How do we separate useful knowledge from a vast amount of useless background noise that is generated without proper vetting and where it is difficult to separate fact from fiction? How do we create new domains of knowledge and new fields of intellectual pursuit from analyzing and properly interpreting data gathered across traditional fields of natural and social sciences and engineering? We must use these tools to ask bigger questions. We can simulate a new range of conditions and test our assumptions more deeply. We can rely on much larger and much more diverse kinds of data to further discoveries in all fields of engineering and to help us predict more reliably what the consequences and spillover effects, including unintended consequences, of the new technologies will be. Your faculty at the Thayer School already know this. The school's no department structure encourages a broad view of engineering thinking. The school already participates in a wide array of research projects that bring in expertise from Dartmouth's renowned humanities and social sciences programs, medical school and business school, among other fields. This interdisciplinary thinking will be valuable in acquiring an awareness of the human elements at play in complex engineered systems. My third and last insight is that our biggest challenges are unfolding in a global context. You are graduating today, leaving a small college town in New Hampshire. Whether you choose to work in New Hampshire, in the US, or in a foreign country, your career and life experiences will be shaped increasingly more strongly by the highly interconnected and networked global enterprise. The good news is that science and engineering are already global enterprises. This too is part of your new era. I want to leave you with 2 sentences. First, global challenges need global solutions. Good engineering anywhere is good for engineering everywhere. No innovation is too small to be useful. Remember that our country's vision of putting man on the moon galvanized an entire generation of engineers and scientists. It transformed our innovation ecosystem. But also remember, as someone noted, that we put man on the moon before we put wheels on the suitcase. Having wheels on the suitcase is also useful in day-to-day lives. So let me leave you with these 3 insights. First, by creatively engaging engineering with the social, behavioral, and economic sciences, we can better understand human interaction with technologies. Second, our new era of engineering and science is offering new tools and big data for observation and interpretation about our world. And these tools need to be carefully employed and managed. And third, our most difficult problems and their solutions are global ones. And working within that global context is essential. Even if you live in a tiny village, think global. I have every confidence that as Thayer School graduates, you are fully prepared to take on the grand challenges and to succeed in the 3 areas that I briefly highlighted. This reminds me of a story about a dinner for Nobel laureates hosted at the White House by President John F. Kennedy. The story goes something like this. President Kennedy apparently marveled at the collective intelligence assembled at the dinner table that day and said, "The last time there was so much intellectual horsepower in this room was when Thomas Jefferson dined alone." When I look at the graduates here, and of course the faculty, there is so much intellectual horsepower in this room. If Kennedy were here today, he would really marvel at your accomplishments and at your potential. And if Thomas Jefferson were here today, he would think that this collective intellectual horsepower was even greater than his own. So looking out at you here today, I have every reason to be optimistic that even the largest and the most daunting challenges will be met and mastered. Congratulations. Thank you very much.